So I'm very excited to be introducing our first keynote speaker, Professor Wolfgang Heidrich. So Wolfgang has been a professor at the King Abdullah University of Science and Technology since 2014, after being faculty for 13 years at the University of British Columbia. So during these years, he has won a multitude of awards, including the Humboldt Research Award and the ACM SIGGRAPH Computer Graphics Achievement Award, as well as being inducted a Fellow of the National Academy of Inventors, IEEE, Optica, AAIA, and Eurographics. His research spans several areas, including computational imaging and optics, of course rendering, computer vision, and inverse problems. And Adrian and I thought it would be great to invite Wolfgang back to EGSR 20 years after his tenure as program chair, so he's run this event as well, to tell us about the synergy between rendering and optics. So with that, I'll let Wolfgang take it over.
Thank you, Yannis. It's great to be back. It's been a while, but I'm looking forward to having communications with you. Okay, so today I want to talk about AI for optics and optics for AI. I mean, my focal point now is in imaging, right? So I will tell you how we can use optics, or we can design optics for imaging. So the first part of the talk will be talking about work that we've done recently. And then in the second part of the talk, I hope I can convince you that as rendering people, you have maybe some technologies that you can contribute towards imaging and on computational optics, and maybe light transport at a different scale than what you've been considering before. So hopefully we can also then continue that discussion in the coming days. Okay, so let me start by motivating basically the computational imaging pipeline. This is kind of the way I think about computational imaging, is that you have a real world scene, and it has rich information, not just a 2D image. It has rich information about 3D geometry. It has appearance, material, spectral information, high dynamic range, all those kinds of things. And in computational imaging, we're trying to come up with an optical design that encodes as much information as possible from this real-world scene onto a 2D image sensor. And then we decode information with some kind of computational module, right? So there's an encoding, and the optics is an encoder, and the computation is a decoder. That's one way to look at it. The other thing that we notice is that the information, the richness of information in the real world is much larger than what we can squeeze onto the 2D image sensor. And so therefore it's actually, you can also think about it as a lossy compression, right? There's a lossy compression happening as you map the scene onto the image sensor. And now, basically then you're decoding a lossy compressed data set. And the question is, where does the missing information come back from? Where do we get it back from? And the idea is, of course, we're going to use some kind of priors, typically data-driven priors these days, that go into this reconstruction method. Now, where computational imaging comes in is when you try to co-design the optics and the decoding, the computational part, in such a way that you make the most use of the bandwidth that you have through your image sensor, right? This is the funnel. And so one way to think about it is that you want the information that comes from the measurement to be as orthogonal to the measurement, to the information that comes from the priors, because it makes no sense that if you have already a bandwidth limited sensing system, that you spend a good chunk of that bandwidth just confirming the priors that you have anyways, right? So you want to basically balance what you can easily do with priors and what you can easily do with the sensing, and really balance these two things off. So let me start by showing you an extreme example of this. So this is a paper published last year from my group, and here we're basically designing an optical system to make use of generative AI to deal with faces in general. So we're going to start with a generative model for faces, okay, and you know all that, okay? So there's a generative model that was basically trained on a huge phase database. So the model takes a tiny latent vector and basically generates realistic looking images. Different latent vectors create different realistic looking images. But once we've trained this model, what we've basically achieved is that this latent space here is basically a semantic encoding of information about faces, right? So what we can do now is we can try and build an optical system that rather than measuring images, it actually measures just that latent vector, okay? And so we're hampered in this attempt by basically the fact that in optics it's very hard to do nonlinear operators, but what we can do is we can basically run linear projections of the image through an optical computing module, basically. Okay, so we're taking our image and we're running it through linear projections, thereby reducing the data quite a bit, and then basically taking that and basically having a little translation network that basically takes this really reduced data amount and translates it into the nonlinear latent space of this generative model. And the data reduction is quite significant. I'll show you some examples in a second. But the idea is that because we're sensing very, very few samples here, this network is actually super lightweight, okay? And so that's the encoding part. And then we can actually reconstruct images, okay? But actually maybe more interesting is we can actually do direct post-analysis directly on the latent space vector. So if we just want to get facial segmentation or facial feature tracking or basically text labels, like whether somebody has bushy eyebrows or not, those kinds of things can be done directly by analyzing just the latent space vectors, right, without any image reconstruction. So we're basically completely sidestepped the image reconstruction task here. And so all of that makes it super lightweight to deal with this sensing in the latent space, okay? So here are some results for that. So this is what the hardest part is actually if you want to reconstruct a realistic looking image, right? So compression, like modest compression ratio, still much better compression ratios than, let's say, normal compressed sensing approaches, but overall relatively modest, produce good results, and then you start losing the identity if you have more aggressive compression ratios. However, if you just want to do facial feature tracking, you can actually go to really extreme compression ratios. And this one here is basically the equivalent of just having 8 pixels in your sensor, okay? So we're basically doing optical projection through like an optical matrix for image space to an 8 vector, then translating that with a really lightweight neural network into the latent space for the generative model, and then analyze that short vector again with a very lightweight neural network. So you can see that the sensing cost is very low. We can do that potentially at very high speed. You can do the processing with really low latency because the data volume is just tiny, basically. And this is basically other results for, compression ratios, right? So, I mean, basically here the text labels are generated with basically the equivalent of, I think, 16 or 32 pixels. So, okay, so basically that's the idea, is that we're talking about optics for AI. We want to basically offload computational costs into the optics domain, right? And typically that means just linear operators. Nonlinear optical computing is something a lot of people are working on, including me and my collaborators, but it's not really ready to talk about. But we can do a lot already with just linear optical processing, right? Because you basically get computation almost for free at the speed of light. There's no power consumption, nothing. It's just basically free. Okay, so that's the first part. So for the rest of this, I just want to talk a little bit more about sort of like a standard workhorse method for dealing with this kind of computational imaging pipeline, which is end-to-end design of optics and computational methods. And here I'm going to use a a motivating example, which is a very, very simple optical design space, okay? And we'll make it more complicated as we go along. But here, basically, the idea is, let's say you want to design a so-called thin plate optical system. So this is a system where you throw away all the complicated lenses from your camera and you just replace this with a single thin piece of glass which has either a diffractive optical element etched into it or a meta surface. Okay, so the two things are actually sort of in many ways equivalent. And so the idea is, so if you know optics, you know you can do a very good lens for a single wavelength, but if you want to do imaging across the whole visible spectrum, you have trade-offs, and then how do you design that, right? And the way this works is, okay, so you have a forward simulator, and spoiler alert, that's going to be differentiable, okay? So we're going to have that, okay? And in this, if you haven't encountered this, so for this particular design space, the forward simulator is essentially a Fourier transform, which corresponds to Fresnel propagation or angular spectrum method or something similar, which basically says you take the height field here, right, which is a scalar array, you do the Fourier transform, and you get basically the point spread function of the system. And so then we take a data-driven approach, right? So we'll take an input image, we convolve it with this simulated point spread function. We get a simulated sensor image. And now you'll see that the sensor image is not the sensor image that you would expect from your cell phone. Okay, so it's not because we are in a very, very simple design space here. Okay, so you will never be getting very, very perfect, very, very high quality raw optical performance out of this design space. However, if we actually design this optical system correctly, then hopefully we can encode enough information and the right kind of information in this sensor image in such a way that the reconstruction algorithm has an easier job, right? And so let's run a reconstruction method. So this is your favorite neural network model for image restoration. And we get an output image, based on the simulated input. And now, of course, we can set up a loss that compares the input and the output, and we backpropagate the gradients and update the neural network weights. But we also update push the gradients all the way through the optical simulation, and we update the design of the optics as well. So this framework allows us to basically find at least locally optimal trade-offs between what you do in optics and what you do in the algorithms, okay? And of course, image data bias, not a single image, right? Okay, so what do we need to make this work? Basically 3 points, okay? One is we need to have a differentiable simulation for whatever optical design space you want to design for, right? I've mentioned one very simple one. The others I'll show you in a second. The second thing you need is you need to have optimization methods that don't get stuck in local minima as you try to optimize your design parameters. And that's actually for anybody who has actually designed an optical system with something like CMAX or whatever, you get stuck in local minimum immediately, right? So just because you have a differentiable simulator doesn't necessarily mean you can find meaningful minima in the inverse design, right? So we all need to overcome local minima and find good global solutions. And then finally, we have neural network architectures for doing the computational part. Now, I'm not going to focus on that because the reality is that there are lots of neural network architectures that are being proposed for different reconstruction tasks, and most of the time you can just start with the best existing models for dealing with hyperspectral images, for example, and plug it into this pipeline and just work with that then. Okay, so let's talk about where we are with respect to these differentiable optical simulations. So I've shown you already basically the diffractive only / meta-lens only kind of design space. It's very simple. It has the advantage that if you're a researcher in a university, you can prototype these kind of devices. You can build these DOEs, for example. If it's meta surfaces, you may have to go external, typically for larger ones, but it's something you can prototype still. It has a lot of applications, so people have shown not just like RGB imaging, but RGB depth imaging, spectral imaging, extended depth of field type of applications, both my group and other groups. Okay, so this, I would say it's pretty much settled. The problem is that because it's such a simple design space, you're not gonna get like cell phone-like image quality out of it, right? So the next thing up is that if you take a DOE or a meta surface and you combine it with classical optics, like refractive optics, in such a way that the refractive optics is responsible for basically focusing the light, which it does very, very well, and then the DOE or the meta optics actually just manipulates the point spread function to provide some additional encoding of the information, let's say spectral information or depth information or things like that. And here's an example from a recent paper. It's a collaboration with Tongji and EPFL. And so basically here, this is revisiting this idea of double helix PSF, right? So this does a depth encoding, right? So for every point, the point spread function is a double helix. And so what that means is if you have a point at a certain depth, it gives you 2 dots, and the orientation of the dots tells you how far away the point is, right? So you get a depth image that you can reconstruct here, and this was used for imaging mouse brains, right? So basically, this works if you assume that your refractive optics is basically, the lenses are basically ideal. Okay, so, and in this setting, for this paper and many others, the optics are ideal because you're in a microscope and you spend tens of thousands of dollars to buy really good microscope objectives and tube lenses and all that other stuff, right? And then this works like a charm. Now, if you want to take this kind of PSF engineering technology and you want to put it in a consumer device or an SLR, you have the problem that the lenses are not ideal. They're aberrated, right? And the aberrations mess with the kinds of PSFs that you want to design. So if you don't even know what the aberrations are of your optical system because you assume perfect lenses, then you're not going to get good performance out of the PSF engineering. So we need to do all this design in such a way that we take real aberrations of real optical systems into account. That's really the key part and the key insight that we had a couple years ago. And since then, we've started really putting a lot of energy into taking this end-to-end design and differentiable design kind of strategy to the space of refractive lenses. And so we have a sequence of papers, and also open source code, by the way, that you can download, the DO system, and also other the follow-up systems that basically a specific ray tracer just for lens design. So you have a differentiable ray tracing engine. You have basically a metric design metric that's based on somehow the final image quality after reconstruction. And then we have a curriculum learning strategy that allows us to actually get out of local minima. And so let me show you what that can do. So here is a design space for, let's say, an SLR camera. Okay, so this is something maybe a lens this size, right? And we have a design space that's only spherical surfaces. Okay, so no aspherics in this example, and we initialize the optical system was just putting flat pieces of glass in, with adding a little bit of randomness to the curvatures, like really small random curvatures, just to break symmetries. And then this optimization runs completely automatically without any manual interaction. Okay, so you're basically getting down to this final design, which has only spherical surfaces. So again, it's a curriculum learning strategy. So basically, it starts with a simple design objective, and then like let's say a narrow field of view, and then it basically adds additional complexity on top of that. And what that means is that overall your optimization landscape gets convexified, and you get a global, some kind of more global optimum, I guess. Okay, so this can also be done for other kind of design spaces. So here is a design space for like what you would get in a cell phone camera, right? So here, the back focal length here is really, really tiny. So you want to squish everything as compact as possible, and that's only you can only do that if you allow non-spherical surfaces. So basically, what's called asphere. So you add polynomial degrees to that, and so here's the optimization for that, or at least the initial parts of the optimization. It's not always also all the way showing all the way to the final result, but you get these crazy shapes, and those are actually the shapes that you do, the kinds of shapes that you do see in cell phone designs, right? So like lenses that have convex and concave regions on the same lens surface, those kinds of things are actually, you carry them around in your pocket. So that's okay. So and we also showed that you can do extended depth of field and other types of applications with that if you adjust the design space appropriately. Now, okay, so now we have refractive lenses. And the next step then is, okay, let's go and put the two things together, right? Because I still want to have the PSFs engineered with diffractive optics, right? So can we put diffractive and refractive optics together? And now, of course, there's this tension between doing simulations in wave optics and doing simulations with ray tracing. We had two papers, SIGGRAPH 24 and then also another paper with 8KU in 2025, where we basically said, okay, the DOE can be the last element in the optical path, so that's kind of a partial solution. One of the things I really want to get to, and what we're working on, is basically I want to be able to describe arbitrary optical systems, right? So you can have two lenses and then a DOE and then another lens and a meta surface and whatever, right? So we can, that's one of the goals, right? So to get to that point, right? But let me talk about actually fabrication a little bit and fabrication-aware design in this context. So one of the things that we always do with this kind of line of research, obviously, we build the DOEs, right? So we have a clean room, a nanofabrication facility at KAUST, and we're actually building these DOEs so that we can have prototypes. And basically, the prototypes tend to kind of work, okay, but there's fabrication error, right? Whenever you do nanofabrication like this, there's fabrication error. So let's say you have a design that was intended to have perfect square features, and what you see is you have these things like this corner rounding effects and maybe some surface roughness kind of effects. And it degrades the quality, right? So one of the things we started really looking into is, can we better predict what is actually going to happen during the fabrication and then compensate for it in the design process, right? So here's the graphical illustration of that, right? So you're running a simulation pipeline, a standard simulation pipeline. You simulate it, you get a really nice hologram in this case, right? And then you build it, and you get something with much, much lower contrast, and diffraction efficiency is just much worse, right? And so in order to explain what's going on here, I'm going to have to go on a little bit on a tangent and tell you a little bit about how we do the nanofabrication. But this is just an example. I mean, there are other nanofabrication pipelines that have similar artifacts, okay? But I just want you to understand what type of artifacts typically come from nanofabrication, okay? So the process that we're using is called direct laser writing followed by nano imprinting. Okay, so that works as follows. So you have a glass substrate down here, and then you have what's called a photoresist, And then you have the direct laser writing part is that you have a laser beam scanning across the surface and depositing a gray level exposure dose onto the photoresist. And so the first thing that you get is that this laser at the scales that we want to fabricate, right? We're right always with this nanofabrication techniques, we're always right up to the physical limits of what the device can do. So you have a blur, okay? Because it's just the fraction limit of the laser introduces a blur. Then the dose, that light actually chemically interacts with the photoresist, right? And it creates chemical changes. And that's a nonlinear process, which I don't know, I can calibrate it, but I don't have an analytical model for that, right? So it's a nonlinear process. The next thing you do is you develop that photoresist, and now that's a 3D chemical interaction between the development agent and this height field that's evolving, right? It's like a complicated three-dimensional interaction of chemicals. And again, I have no idea how to come up with an analytical model or something like that, right? So it's just a development process. Happens to be local. It's local, right? Because all the chemical interactions are always local, right? So, but it's really complicated if you wanted to model it analytically. And then the final step is you fill the whole thing up with a photoresist, okay? Not with a photoresist, with a photoresin, and then you cure the photoresin. That's the nano imprinting step, and you lift that off. And if you want to just have one DOE, you're done, okay? And if you want to build 100 DOEs or 1 million DOEs, then you can basically use this thing as a stamp and then use nano imprinting on that stamp to do your mass production, basically. Okay, so it's basically very close to a mass production process that you can already do here, okay? But what you need to be aware of is that when you actually cure this photoresin, there's some volume shrinkage and all that kind of stuff. So again, really messy kind of shape changes, okay? So, right, so what we want to do is we basically want to do fabrication-aware design, which is, I would say, a step up from computational lithography. A lot of people are thinking about computational lithography in the context of chip manufacturing. We can do it for this optical device manufacturing as well. And we can push it beyond that to fabrication-aware design, okay? So computational lithography, basically the idea is as follows. So you start with some kind of a design process, right? It's either the end-to-end design process for an optical device that I've described earlier. So either automatic or some manual process or an analytical function, whatever it may be. And you have a design, and then you hand this design off to a foundry that builds the device for you. And then the foundry runs some neural lithography model where they basically have a characterization of their fabrication process, and they tweak the design files, right, in such a way that the geometry that you get out is as close as possible to the design to the designed geometry. Now the problem with that is that you will never hit that exactly. Never. The diffraction limit is just a fact, and that means you never get geometrically square features, for example, right? It just never happens. The only question is, how big is the corner rounding, right? You can reduce it, but it's always going to be there. And if you have an analog computing system or an analog lens, these differences already matter, right? So you really need to account for them. So what we're trying to do in fabrication-aware design is basically that we try to basically merge these two things together. We want to break down the barrier between the design and the fabrication unit. Okay, so we'll basically have the design pipeline. This is basically what I explained to you, in the first at the beginning of the talk, right? So we have an end-to-end design with reconstruction, whatever, and we arrive at a geometry. And then now what we do is we have a digital twin of the fabrication process, and we're basically backpropagating the gradients through that to actually update the design files that we send into the fabrication process, right? So this digital twin on the forward path, it takes whatever design files you give it, and it gives you a very, very detailed, like sub-micron geometry of of the shape that you will get out. And then you can use that shape with your optical simulation to see if you have a good, well-performing lens or a well-performing hologram or whatever. And then you backpropagate the gradients through to update the target shape and then the design files. And what that means is that you always stay, whenever you do this thing, you always stay within the space of shapes that is actually feasible with your fabrication process, right? You never go outside of that envelope. And that's basically what you get from that. So basically, again, a conventional pipeline and the fabrication-aware pipeline. On the left, the conventional, if you design it, it says, okay, it will work really great. And in the fabrication-aware will also say, okay, it will work really great. If you look very carefully and if the display is calibrated the right way, well, actually here it's a bit amplified. It's a little bit more noisy, actually. So the image quality that this design process predicts is actually not quite as good as the idealized one, but it's realistic, right? It's what you can achieve with your fabrication process, and so so when you actually build it, you actually get what you designed, right? So that's the idea, right? And we can do that, in parallel. So I think this was, when this was published, this was probably the largest, as to my knowledge, this was the largest digital hologram ever designed and produced, 10 gigapixel hologram. This, again, classical design and the fabrication of a design. And again, it's not just holograms. We want to do this for lenses, right? So let's go back to the initial problem of designing a thin plate optical system. And basically, with a conventional process, right, if we just build a DOE with a conventional pipeline and then try to deconvolve with what we think the PSF of that system is, then the image quality is very bad. And so what you have to do is you basically have to build the system, then try to calibrate the PSF somehow, and then actually do the reconstruction with a calibrated PSF rather than the designed PSF. And then the question is, well, did your design actually do something for you, or is it because it's actually going to be a different PSF, right? Whereas if we do that with fabrication-aware design, this is the deconvolution just with the simulated PSF. And the deconvolution here is not even a very sophisticated heavy neural model. This is actually just a Wiener filter, okay? So Wiener filter with a with a good PSF model actually can produce very good results in this situation. And of course, you can do even better if you have a neural network, but the neural network doesn't need to be very heavy. That's the key point here, is we can keep the compute pretty low profile so that we can actually do this reconstruction on a mobile platform, for example. Okay? All right, so, wait, how are we doing on time? Okay, so, all right. So, the final thing I want to talk about in terms of, past work is, so what I'm also interested in is how we can incorporate new types of evolving optical components in these kind of imaging systems. So this was a paper we presented last year at SIGGRAPH Asia, and it actually won the Best Paper Award there, about foveated imaging, right? So foveated imaging is that, as you know, your eye is does not have uniformly high resolution, right? It basically scans across, and then the fovea is the region where you have maximum resolution, and it scans across, and then that's how you build up an image. Now, the way we do that in a computational camera system is that, let's say we have a very simple optical system, like just a simple, a single refractive lens. We can add what's called a dynamic faceplate in front of it, and it's basically a programmable. If you know deformable mirrors, like from astronomy, they're basically the same thing, but in a transmissive way, okay? So basically, you can program aberration corrections into the DPP. It's transmissive, so it actually supports relatively compact form factors. And then you can correct aberrations, not for the whole image plane at the same time, but for each image region at a time, for example, right? So here's the example for that. So we can basically stack up in focus image by basically taking multiple images with different aberration corrections for different image regions. And so this is what this looks like in PSF space. So if you have just the static lens, the PSFs get progressively worse. The aberrations are really bad in the corners, right? But if you actually have a DPP and you correct, you can actually basically remove all the aberrations, even far into the corner, right? But you make other image regions worse, so basically then you can stack up the images to get an all-in-focus image. But maybe more interesting for if you have, let's say, a robotic system or some other kind of real-time system, you can actually combine this with some kind of a tracking approach, right? So where basically the low-resolution blurry image that you get without any aberration correction is maybe good enough for you to tell where the objects of interest are, and then you track them and you correct the aberrations just for that region of interest, right? So that's one of the things you can do. Okay, so that's the first part. Okay, that's the past. That's the past. Okay, so let me tell you a little bit about where I think so first of all, where my research is going and where I think that maybe the rendering community can help out with some computational light transport problems that really need to be solved if we want to have this scale to the max. Okay, so here's kind of how mental diagram of how I think about my research agenda these days. So first of all, we have the bottom layer, which is basically computational light transport. So this is basically simulating light transport at different scales and actually across scales with very, very high accuracy. Okay, so combining ray tracing, scalar diffraction models, maybe full wave simulations. And the scale differences are really massive. So this is a really difficult problem. Okay, then on top of that, we can basically characterize different nanofabrication processes. I've shown you one. And then basically what that means is we can actually build or we can design devices that will perform, that will actually in reality perform as designed, right? That's really a big, what you need in order to actually have some commercial product in the space. You cannot afford to build something and for a consumer device and then calibrate a different PSF for every device or something like that. You need to make that predictable, right? So that's kind of the next layer. And then on top of that, there's computational imaging system. So this is the actual system for, let's say, for spectral imaging, for extended depth of field imaging, for, more compact cell phone cameras, all those kinds of things, but also microscopy applications and other biomedical, so lots of applications in that space. And then finally, also optical computing. So basically the idea that you want to implement matrices or other nonlinear operators, ideally in such a way that again you build them and you get the matrix you designed, not some other closely related but different matrix, right? So that sits on top as well. Okay, so we're just talking about the bottom layer, the computational light transport. Here's basically the stack of scales. And that's really what makes things really complicated, right? So we're basically, if we want to do meta optics, we have to design things at like the nanometer scale. And if you want to put together optical systems, we have to simulate things at the centimeter or meter scale. And that's like 9 or 10 orders of magnitude. If you want to do full wave simulation, let's say, you typically work with grid resolutions of like 10 nanometers or whatever, right? So you have exavoxels if you wanted to discretize the whole space in a brute force way. So that's clearly not feasible, right? So let me go over this hierarchy real quickly. So paraxial optics, if you haven't seen that, In optics, oftentimes people will call an optical design process ray tracing, but it's really just using these 2x2 matrices, ABCD matrices. So if you haven't seen that, this is actually really useful for designing like overall layouts of optics and stuff like that. So that might be something you should look at. The next thing down is then geometric optics, right, which is what we call what we call ray tracing in computer graphics. And so the nice thing here is we have real aberration, real lenses with real aberrations. They can capture all these kinds of higher order optical aberrations correctly. It works for coherent and incoherent light, so that's really nice. But it lacks the diffraction effects, and it lacks the ability to deal directly with DOEs and metasurfaces and other hybrid optical systems, right? So then, next down is these scalar diffraction models, right? So basically where there's like Fresnel propagation, angular spectrum method, Rayleigh-Sommerfeld integral, all those kinds of things. They're working with DOEs. They make the so-called thin plate assumption, which I'll get to. Which is a simplifying assumption, but if the simplifying assumption is valid, you have no accurate diffraction models. With scalar diffraction, you don't have polarization. That can be a problem because actually, if you bend light a lot, you automatically always get polarization effect as well. Okay, so you really cannot separate the two things. So people upgraded to vectorial diffraction. Okay, so now you have you basically vectorial versions of ASM, Debye integral, all these kind of other kinds of models. One problem with these kind of diffraction models is they're actually coherent light only, right? You're always simulating one wavelength, and if you're trying to design an imaging system that replaces a camera that works in this room, what you need to do is you need to integrate over multiple different wavelengths to have like an incoherent average. So it's kind of ridiculous because you have to do these super high precision simulations, and then you have to do hundreds of them potentially in order to simulate the incoherent the nature of light. And if you do vectorial diffraction, it's even worse because now you have to also integrate over all the possible polarization states as well. Okay, so it's really expensive. So one of the things that we really need to get to is basically how can you actually accurately propagate waves through incoherent light through DOEs, for example, right? That's actually a big problem, and it's different from the diffraction models developed in computer graphics, right? Because precision really matters here, right? So if you have a 1 centimeter aperture and let's say a couple centimeters propagation distance, and you want to know whether the light hits this pixel or that pixel of your image sensor, I mean, that's a couple hundred microradians of angular resolution that you need, right? So you need to be very, very accurate still, even though you're integrating over all these wavelengths. So it's actually a really tough problem. Okay, so let me talk about this thin plate approximation. So in computer graphics terms, we're ignoring shadowing and masking typically. Okay, so your DOE is a height field, and so for normal incidents, there is no shadowing and masking. But if you go off axis, there is shadowing and masking. Things bounce off your sidewalls of the DOEs. Actually, completely ignored right now for DOEs. Right, completely ignored. The other thing is that the phase delay is actually different, and that's the bottom part here, right? So basically, you have a nominal. What you do when you design DOEs is you basically say, okay, I have an optical thickness. I map the optical thickness to a phase. And then that phase is applied to my wave, independent of whether the wave comes from normal incidence or from 30 degrees off. So you're basically missing a cosine term there, okay, or completely ignored. Okay, so we have work to do. Okay, so we really have work to do, right? So there's like in a height field like this upper one, right? There could be interreflections, all those kinds of things. which you can't do, you just can't do with scalar diffraction, right, or vectorial diffraction. So if you want to move to capture that, you have to go to basically full wave simulation, what's called full wave simulation, right? So Maxwell's simulation of Maxwell equations. This is typically used for meta surfaces, right? So it's like FDDT or RCWA or other types of solvers. So they're basically discretizing the space into sub-wavelength unit cells, and that means what that means is that you can really simulate only very, very small domains, right? So it's really, really really limited in simulating large-scale devices. But it's done for meta surfaces, right? So, so the way we design meta surfaces is that a meta lens, if you wanted to simulate, I mean, theoretically, you could build whatever you want over your 1 centimeter or 5 centimeter or whatever aperture. But in order to keep the computation, feasible, we're breaking things down into unit cells, right? So basically, and for each unit cell, we have sort of like a nanoatom that replace. Okay, so the nanoatom could be, for example, a circular nanopillar like in this design, or it could be more like a rectangular shape like in this design. And then what we do is we're basically pre-computing for this particular nanostructure with a particular diameter, what is the phase profile or what is the polarization effect for that particular nanostructure. The problem is when we do this pre-computation, we're basically tiling the whole plane infinitely with the same nanostructure, right? With the same nanopillar here. And then we say, okay, well, that's phase pi, and nanopillar is phase 2 pi, and then we put them right next to each other because here we want to have a modulation of pi, and here we want to have a modulation of 2 pi, so we just place the nanostructures right next to each other in a completely different neighborhood than what was ever simulated, right? And so that for some nanostructures, this can be a big problem because again, there are actually different types of meta surfaces. Some of them are quite where some of them are basically acting more like light guides, then you can get away with it. But some of them are like basically little nano antennas, and there's a lot of resonances between them and standing waves, and they're slowing down different modes. And so now, if you change your environment, you put a big one right next to a small one, or if you rotate the same nanostructure by 30 degrees, right? The interactions are completely different from anything you've ever simulated, and that actually really restricts the performance as well. So, yeah, and then so in silicon photonics, people don't need to do that, right? In silicon photonics, people actually do design just, basically a volume of material yes or material no, like two materials or in like a pixel fashion, right? And this is small enough that you can do inverse design with something like FDDT for like basically splitting red and blue light coming through a fiber, right? So you have, for communication devices, you have two wavelengths coming in from the fiber here, and afterwards the red goes here and the blue goes here, right? So this you can do, this scale you can do, right? But this is basically the whole thing is maybe, I don't know, a couple microns, or if that, right? So really, really tiny, really tiny devices, right? But how can we do something large scale with that? Okay. So, all right, so that's basically my list of open problems for optical simulation. So basically, it's all related to bridging these kind of dimensions, right? Bridging geometric optics and scalar vectorial diffraction for simulating hybrid optical systems, broadband propagation and incoherent simulation for these kinds of DOEs. The next thing is bridging scalar and vectorial diffraction and full wave simulation. So basically, that means getting rid of the thin plate approximation, modeling standing waves between deep valleys in a DOE, for example, reflections off of sidewalls, all that kind of stuff. And of course, again, doing that in a reasonably efficient way overcoming this kind of unit cell tiling issues. And then, that's the medium term, right? If you can, then the question is how deep down the rabbit hole you want to go, right? Because now you can go branch out into like nonlinear optics and like quantum states, right? Like there's this squeezed light where basically you have less uncertainty in the phase than in the amplitude, or the other way around, right? So basically you can do a lot of stuff if you're really willing to do a deep dive on any one of these effects and then incorporate them into your imaging systems. Okay, so really quickly, just 2 slides on the more higher level structures. I mean, I have actually one, just the imaging system. So basically, for the imaging systems, what I want to see is miniaturized hybrid optics, right? So basically, I think cell phones in a couple of years will have combinations of diffractive and refractive optics, because that's the only way you can get the same performance with smaller form factor, or better performance with the same form factor. I also think these application-specific imaging systems or sensing systems will play an important role in the future. There are many cameras now that will only ever image one particular type of scene, right? Like, think of an eye tracker in a head-mounted display, right? It does not need to be good at imaging general scenes. It just needs to track eyes really, really well, right? So these kinds of ideas work there. Biomedical applications, a lot of really interesting things in microscopy and super resolution, face imaging, those kinds of things. And then also metrology and lithography, so using computational imaging systems for actually characterizing your nanofabrication facilities, etc. So anyway, I'll stop here. Just a quick pitch for if you go to SIGGRAPH, there's actually this graphics for science workshop on the Monday of the SIGGRAPH conference. I'm not I'm not an organizer. I'm a keynote speaker there. So don't go for my talk because you probably just saw it. But there might be other talks that you might find interesting. And with that, thank you very much.
All right. Thank you, Wolfgang, for this fascinating talk. Any questions from the audience?
I had a question about, the spinning sort of lens that you used for the foveated.
Yeah, for the foveated, yeah.
Have you ever tried using that for something like depth estimation? Because you can get depth from focus by saying, okay, well...
Right. So actually, we have different applications in the paper. I just didn't want to present the whole paper here. One of them is we actually have calibrated 3D PSFs, so you can actually, if you know where you are in 3D space, you can focus at that depth, but you could also use it for depth estimation. I mean, we're following up on this kind of concept, but I agree. It's sort of it's one of the obvious next steps is to look at like depth and depth, both extended depth of field and depth decoding, depth imaging, right? Both of them, right, can benefit from this kind of approach. Yeah.
And what is the power draw for that? Is it costly compared to like a depth camera or some? I guess it can do lots of different things, but
sorry, I didn't catch that.
How much power does it use to?
So right. I mean, so it's not a. I mean, it's electrostatic, so it's not a huge power consumption, but you need high voltages. Okay. So right now, and by the way, right now, this is not some technology that you would be able to put in a cell phone. However, it's ultimately not all that much different from liquid lenses. And liquid lenses also started, this form factor and costing a couple $1,000s. And now there's actually cell phones that have liquid lenses for focusing. So we're hoping that this kind of device will go through a similar trajectory if you show that the applications exist, So, and that's kind of one of the things we're interested in. Yeah.
Thank you.
So for your clean room activities, there's some people who do hackathons stuff. So in their garage, they do silicon fabrication.
Right.
Do you have any ongoing research in stuff like that, so making fab cheaper, basically?
Yeah. No, I think that's actually really that is definitely something you can work with. I mean, you can compensate for expensive hardware to some degree with the right software stack, right? So basically, the hardware basically buys you really, really tight point spread functions and all that kind of stuff. But if you don't have that, then you can actually compensate for that by basically doing computational lithography. So yeah, so I think there's a lot of synergy with that kind of stuff. I think the problem is, so there's precision and there's accuracy, right? And repeatability, right? So I think, what's hard to do in a garage for nanofabrication is just even have a repeatable process, right? So basically the variance on the shapes that you get out of the process are pretty high, and then it becomes a little bit tricky. You need, I mean, realistically, you need at least like a temperature-controlled environment and stuff like that to not have, different material expansions and stuff like that. But yeah.
Cool. Thank you.
Hi, thank you for the presentation. What I've seen mostly in your slides are ordered metasurfaces, basically, for metal lenses, which is fairly common, I would say.
Sorry? What's this?
You talk mostly about ordered metasurface, right? Have you looked into disordered metasurface?
Oh yeah, right.
For
so,
light trend control?
Right. So again, that's the thing, right? I mean, basically the moment you have these unit cells, you have ordered, right? And then disordered is stuff like this, where you have the wavelength sorting. The problem is just that the design processes for this don't scale up, right? So it's not like people love unit cells, but it's the only way we know how to deal with metasurface design right now that works for large-scale devices, right? Yeah.
Okay, in a disordered metasurface, we also have a supercell approach that basically we do a unit cell, but slightly bigger with a bit of disorder.
Right.
Have you looked into that?
Okay, but I mean, it's in a way it's still a unit cell. I mean, I know that. So, for example, there are unit cells where rather than putting a single nanopillar down, you put multiple ones down, and they have different dimensions and whatever, and then you simulate that parameter space. But again, with an infinite tiling, right? So in this situation, it's even worse if you have like, a rectangular shape and a cylindrical shape and the different orientations and scalings or whatever. You simulated that on an infinite tiling, and then you put it together with different diameters and next to each other. Then actually the tiling artifacts are actually worse than if you just have a single nanostructure per unit cell.
Yeah. Okay. Yeah. I was wondering if you find some way to balance this defect, let's say.
Well, I mean, well, again, so there are different kinds of metasurfaces, let's say different materials also that you can use. And so basically one of the things that people do if they want to design a large-scale meta lens, for example, is to just say, okay, we're going to avoid materials that have a tight coupling, right, where there's basically a lot of resonances between neighboring unit cells. We're going to shape spaces that discourage that from happening. But then that means you give up also potential capabilities, right? So yeah, we can make do, right? Right now, I mean, people build these kind of meta lenses, but it's just you could do so much more. The bottleneck is not the fabrication in many ways. The bottleneck is really the design process, right? So let's work on that.
Okay, thank you very much.
I'll ask a question. Here.
Oh. Sorry. Sorry.
So you spoke about fabrication, and if I understood correctly, you focused mostly on feasibility, like make sure that what I design is within the fabrication space of the method I use. But there is also the tolerancing issue, right? The fact that a design that may be feasible, I will send it to the machine, to the fab lab, and what I'll get back will not match what I actually wanted to fabricate. Yeah. So what are your thoughts on that? Is that a problem that, well, first of all, is it a critical problem, and can rendering help with that at all?
I mean, with optics generally, tolerancing is an important problem. Even for lenses, when you do the design, you want to make sure that you want to make sure your design is not super sensitive to anyone's curvature and whatever. The really cool thing about differentiable simulation is, well, you know the gradient, so I can tell you exactly how sensitive my image is with respect to this lens curvature, right? Now, for nanofabrication, it's a little bit more subtle. I mean, so basically, repeatability is still. I mean, in order to get really good predictable results, repeatability is important. Now, I mean, if you want to do it in your garage, you don't have the repeatability, right? So then you need to play tricks. You need to train, maybe do the design by sampling different variations of what can go wrong, and then you basically need to have in the neural network, that reconstruction neural network for an imaging system, for example, you need to make the neural network be able to cope with different kind of hardwares and stuff like that. So you can cope with that. If you have a professional nanofabrication facility, even like a university one, the repeatability can actually be very, very good. So just let me tell you about. So we're for our nanofabrication pipeline, right? We had a calibration. We calibrated the system. We wrote the Sigma Fascia paper. We submitted all that kind of stuff. Then there was a shutdown of the nanofabrication facility for 2 months for equipment maintenance and upgrade. When it came back up, we tried the same calibration, and we only had on the lenses a loss of 1.5 dB. And so, you know, that's not horrible at all, right? So and of course we recalibrated afterward anyways to get the 1.5 dB back. But so if you have professional nanofabrication equipment, then the repeatability is usually quite good, you know. So yeah, that's at least our experience.
I guess I'll ask one more question. So we see a lot of sensing, both optical sensing and also other forms of sensing that combines optical components with other stuff. So something I have experience with is tactile sensor, which a lot of them usually have some camera inside and they see how a surface deforms and so on, vibration sensing. But also when I speak to people in photonics, they tell me that a photonic device is so complex that you have the wave optical thing at the top, but then you also have, I don't know, like LC cells that you need to simulate and some electrical stuff beyond. So all of these seem to hint that to be able to do simulation for design, we need to do not just rendering, but also a whole bunch of other effects. Mechanical, again, LC cells I don't really know much about, and so on. So what do you see there as big challenges, big opportunities?
I'll add one other one, which is basically even if you want to design a camera, right? You use an image sensor, right? Why? I mean, can't we design the image sensor layout, or not just the like geometric layout, but actually the electrical function of the image sensor to actually help with this as well? The problem is, I think as a long-term goal, that's where we want to end up. I mean, I don't really know how to get there right now, because basically a lot of these spaces are very hard to parameterize, and then in such a way that you can actually make progress, right? I mean, so basically the people who design image sensors, it's a lot of experience and manual layout of wires and all that kind of stuff. So how do you make that differentiable and I mean, for liquid crystal cells and stuff like that, I mean, people typically do So there's commercial software that does the simulation. They don't do it in a differentiable way. So right now it's not easy to plug that in. But I mean, maybe this is something for the open source community, right? It's basically have put Synopsys out of business. And
I mean, it's not even very scalable, let alone differentiability,
exactly.
right?
No,
Usually,
agree,
you need you simulate some toy LC cell that's way smaller than what you are actually trying to use.
Yeah, I know. And then, exactly. So a lot of it under the hood does also full wave simulation for a lot of these things, right? You simulate a single LC crystal with full waves with FTDT or something like that, right? So, lots of work to do.
All right. Any last questions? Great. So let's thank our speaker again.
Thank you.